Morning class, this is gravitation part 5 video, and today we will discuss on how this acceleration due to gravitation changes due to the earth's diurnal motion. We will discuss that what is the diurnal motion. This is the rotational motion of the earth about its own axis. Now this is the elliptical path, and earth used to move along this elliptical path around this sun, and this takes 365 days. Now again earth also have a rotational motion about its own axis, and this takes 24 hours. This is the diurnal motion, and this diurnal motion has an effect on the gravitational acceleration. Next important thing is centrifugal force. Now what is the force? This is a force arising from the body's inertia, which appears to act on a body moving in a circular path and is directed away from the center around which the body is moving. Suppose this is a circular path. This is the center of this circular path. A body m of mass m is moving around this circular path. Then due to this centrifugal force, this body of mass m will be affected by a force m omega square r, because we can see that the value of this centrifugal force is m omega square r, where m is the mass of the object, omega is the angular velocity of the object, and r is the radius of this circular path. That is, if it is the center and this is the path, then this is the radius of the circular path. So if any object is moving along this circular path, then due to this centrifugal force it will feel a force m omega square r, which will be away from the center, which is directed away from the center. This is m omega square r. This is the centrifugal force on any object which is moving in a circular path. It is said that this force arising from the body's inertia. Now what is the inertia? If any object is at rest with time, then it will remain in that state, and if any object is moving along a straight line with uniform motion, then it will keep continuing this motion unless there is an external force. This is the inertia of a body, and due to this inertia this centrifugal force arises. Suppose this is the earth, and this is the object of mass m, which is situated on the earth's surface. Now if this earth is rotating about its own axis with the angular velocity omega, then any object on this earth's surface will also rotate with the same angular velocity omega as the earth is rotating about its axis. Then due to this centrifugal force, as we can say that the value is m omega square r, this object of mass m will will also feel a centrifugal force, which will be m omega square r, and it will be directed away from the center. And r, here r is the distance of this object and the axis ns, we may say this ns, and also we can say that the gravitational pull on this object of mass m will be towards its center, which is mg. We will discuss the effect of earth's diurnal motion, and this is the diagram where we can see that this is the earth and this is the axis ns, because this is the south pole and this is the north pole. This is the axis ns about which the earth is rotating in this direction, and the angular velocity is omega. Now suppose any object is placed at A, on the Earth's surface, whose mass is m. Now, the latitude of the point A on the Earth's surface is theta. How do we get theta? First of all, we have to draw a line, that is PA. We have to draw a line PA from the axis to that point A, and we have to join the point A and the center with another line, which is R, and here R is the radius of the Earth. So, here this PA, which we denoted as, which I am denoting as small r, here this small r and this capital R is making an angle theta, and this theta is the latitude of the place A. Now, as I said before, that the centrifugal force, due to this rotational motion of this object along with the Earth, is m omega square r, and it will be directed in a direction outward from the center, and the weight or the gravitational pull on this object will be towards the center, which is mg. Now, here r equals to, small r equals to r cos theta. How we can get this? Suppose this is the triangle OPA. We can draw it here, where AP is the base, OP is the perpendicular, and AO is the hypotenuse. Now, what is cos theta? That is base by hypotenuse. And now, what is the base? That is AP or PA. And what is the hypotenuse? That is OA. And the angle, that is PAO, we can see it from here also, that PAO equals to theta. So, cos theta equals to base by hypotenuse equals to AP by OA. And what is AP? AP is small r, and what is OA? That is capital R. So, here we get that cos theta equals to small r by r. So, small r equals to r cos theta. Now, here this line and this line crosses each other. So, if this angle is theta, then this angle will be also theta, and if this m omega square r is the centrifugal force, then the component along this direction is m omega square r cos theta. That is, if small r equals to r cos theta, then m omega square r cos theta can be written as m omega square, r means r cos theta, that is r cos theta into this theta, that is cos square theta, that is it will be m omega square r cos square theta. Now, here on this object of mass m, two types of force is acting on it. One is centrifugal force, that is m omega square r, or if we consider this component, that is m omega square r cos theta along this direction, and another is the gravitational pull mg along this direction. So, the resultant force that the object is actually having is F equals to mg minus m omega square r cos square theta. This is the resultant force, and this is the direction of this force is along the center, because the value of this gravitational pull is much more than this m omega square r cos square theta. Now, we can write it like this. If we take mg as common, then we will have 1 minus omega square r cos square theta by g, and if we take m in this side, then it will be f by m g into 1 minus omega square r cos square theta by g, and we can write this portion as G dash. Now, this is the gravitational force, this G dash is the gravitational force due to this diurnal motion, and we can see from these two, or from here we can see that G is greater than G dash. Now, from this equation we can see that this G varies with the value of theta, because here omega, r and this G are constant terms. So, in polar region, that is this north pole and this south pole, the latitude of this polar region is 90 degree, that is theta equals to 90 degree here, and we know that cos 90 equals to 0. So, in this case, in case of polar region, this G becomes, this equation becomes 1 minus omega square r G dot 0, that is it will be G. So, here G will be G dash, that is here the gravitational acceleration will remain small g, there will be no change of this gravitational acceleration. Now, here for equatorial region, that is the region, this region, here the latitude is 0 degree, that is cos 0 equals to 1. So, this equation becomes G into 1 minus omega square r by G, as cos square theta equals to 1 now. This is the G dash. So, here we can see that the reduction in this gravitational acceleration is maximum in this equatorial region. So, we can say that there will be no change in the gravitational acceleration in the polar regions, and the reduction will be maximum in the equatorial region, and the regions between these places, that is the polar and this equatorial places, this region will have its gravitational acceleration between this G and this G dash.